graph decompositions and their algorithmic applications. Okay, we have two types of graph decomposition. One is called separator decomposition. That is actually known from 1980. Here, we find small separators such that we can break the graph into a smaller and smaller piece, such that at the end, each part of the graph that remains is a small graph. And then we will often solve some problem on that, and then we combine the solutions to obtain a solution for the whole graph. So the new one that actually we considered it more and we developed it more, it's called simplifying decomposition. Here we don't try to essentially, at least not necessarily, we try to cut the graph into small pieces. However, we try to cut the graph, and the cut can be quite large, but we want to get pieces like here. These pieces are not necessarily small, but they are algorithmically simple. And I will define what's the meaning of algorithmically simple later. So it means that now we can solve the problem on each of them, and then somehow we can also combine through these large cuts, at least for several problems, to get a result, a solution for the whole graph. Okay, so that's the general idea of the meaning of the graph decomposition. But before that, I need to introduce a few concepts. What's the meaning of minor? We say that a graph H, a small graph, is a minor of a graph G if we can obtain H from G from these two simple operations. At each stage, you consider one edge, either you will delete it here, or you may contract this edge. When you contract it, then you may remove all self loops or multiple edges, and you just keep one edge. For example, as you can see here, there is a K-tree graph, a bipartite graph with 3 vertices on each part, which is a minor of this big graph. That's essentially called the map graph of US. And you can see each edge essentially you can get from contraction of which part of the graph. And if you know or you remember from the Kuratowski theorem, we know that a graph is a planar. Namely, it can be embedded in a plane with no crossing if and only if it does not have K-tree, namely this graph, or K5, a complete graph on 5 vertices, as a minor. So that's the Kuratowski theorem. So minor is a very old concept. And indeed, there are these graph minors. Probably I will say that's the deepest theory in graph theory, which is essentially introduced by Robertson and Seymour since 1983 in like maybe 23 papers over 25 years, and some of the papers are like, I don't know, 100 pages. I think the total of the project may be around 700 pages. Very complicated stuff essentially, and relatively old stuff. And the main reason essentially to prove this Wagner's conjecture that essentially says for every finite set of finite graphs, every finite set of finite graphs, one of its members is isomorphic to a minor of the another one. Or essentially, one member is a minor of the other one if you consider a large sequence. Anyhow, that's the whole goal. But during this goal, during this project, they have developed several concepts and several theorems that are very useful for algorithm design. Okay, so that's about minor, graph minor, and now tree-widths. Tree-widths actually is the measure of similarity of a graph to a tree. So, namely, trees have tree-widths 1, series parallel graphs have tree-widths 2, and complete graph on n vertices have tree widths n minus 1. More precisely, tree widths of a graph is the smallest possible width of a tree decomposition. And what's the meaning of a tree decomposition? So a tree decomposition essentially of a graph is a tree such that we will smear each vertex over some subtree of this graph, such that we have this property. Any two adjacent vertices here, for example, the corresponding subtree here have at least one vertex in common, as you can see here. So for example, here it is the tree decomposition of this graph. And the width of the tree decomposition is called the maximum overlap of these trees minus 1. For example, here the maximum overlap is 1, 2, 3, 4. So the tree width would be 3. Tree width of this graph. Now, so this is some definition. You really don't need to know the exact definition for the sake of this talk. However, the thing that you need to know is that graphs with a small tree widths are like trees. Again, if you know algorithmically, or if you have some algorithm background, you know that almost all problems, all NP-hard problems, can be solved on trees very efficiently. And by very efficiently, I mean you can have a polynomial time algorithm. The same thing happens when the tree widths of the graph is bounded. For almost all problems, not all problems that you can solve on trees, but almost all problems that you can solve on trees, you can solve also them on graphs of bounded tree widths in polynomial time. And that's the interesting things about the tree widths. And again, another interesting thing about the tree widths is the major tool in graph miner theory of Robertson and Simmer. So they are using it a lot. And it's a very important concept. And these are exactly the part that I have mentioned. If you remember, I mentioned that we try to decompose the graph such that each of them is algorithmically simple. And by algorithmically simple, I mean they should have bounded trees. Okay, so what are the algorithmic goals that we are considering in this talk? So we often have three algorithmic goals. One is that we want to find, for some problem, we want to be correct, means we want to find the optimum solution. We want to do it fast. Fast means polynomial time algorithm, not trying every possibility, which is exponential. And then we want to solve a hard problem. By hard problem means NP-hard problem, because some problems, you know, they are polynomial time algorithms, and one of the most complicated one that there is a polynomial time algorithm for that is the maximum matching in a weighted graph. But these are the problems, and lots of practical problems are indeed NP-hard or hard problems. For this problem, we cannot solve them in polynomial time unless p is equal to NP. That we don't expect to happen, at least soon, if ever. So these are the three goals that we have. And assuming, as I mentioned, p not equal to NP, we cannot have all of them. We cannot have polynomial time algorithm for NP-hard problems which are optimum. This is simply impossible if p is not equal to NP. Now, we need to consider any two goals, for example, and remove the third goal. For example, if we don't consider the third goal hard problem, then we have an optimal solution for in polynomial time algorithm. That's the one that I mentioned. That's most early algorithm. The most complicated one is the maximum matching or matroid intersection. And most of undergraduate algorithms are indeed belong to this class. The other one that we like more are those that are fast means polynomial time algorithm and for NP-hard problems. Of course, then we need to lose something. And what do we need to lose? The one that we need to lose is the correctness. Okay, we don't want to also lose it too much. So we say, okay, we don't want necessarily to get the optimal solution, but what about a near optimal solution? For example, we want to find a solution in polynomial time for NP-hard problems which is near optimal. By near optimal, we mean maybe the factor 1.5 to 100, maybe log n is the number of vertices. I don't know, n to the 1/3 or something like that. Or the best type of approximation algorithm that we can have are polynomial time approximation scheme. What's the meaning of that? It means that for any constant epsilon or for any epsilon greater than 0, we can get 1 plus epsilon approximation. Okay, so that seems ideal because if epsilon goes to 0, then we should get essentially 1, factor 1, which means optimal solution. But the catch is that when epsilon becomes 0, usually the running time of this algorithm is proportional to the 1 over epsilon. Or they are something like 2 to the 1 over epsilon, or like some kinds of, say 2 to the 1 over epsilon. And if epsilon becomes very small, then 2 to the 1 over epsilon becomes very large. That's the reason that we cannot get it for lots of problems. And again, p-tasks, if we can get for some problem, that would be a surprise. Usually we cannot get it, but in this talk I will present lots of problems that we can get p-tasks for nice set of problems. Okay, so approximation algorithm, very important area of algorithm design. And the other one is the fixed parameter algorithm. That's actually introduced by Donny and Flo in 1999. And here, again, the goal that we want to cross it out is the fast algorithm. Say, okay, we cannot get polynomial time algorithm. We want to find the optimum solution for NP-hard problems. Again, for this problem, say, you want to see whether the graph has a solution of size k. One naive idea is to try every subset of size k. The running time would be n to the k. We don't want to have just some trivial algorithm. We want to have some non-trivial algorithm. Something which is not n to the k, but we want to get it. So if k is the size of the optimum solution, we want to get the optimum solution, not n to the k, but in f of k times n. So f of k times n to some constant, here is 1, which is independent of k. So would be the running time would be f of k times n maybe, or n to the 2 or n to the 3. So this 3 should be independent of k. So as you see, then the running time here, the graph can be very large, and the solution can be small, still we can have a very good running time for this algorithm. However, in this case, even if n is large and the solution is just, I don't know, 10, then the running time is already horrible. But here it can be very good. Even this one, at least theoretically, nice. So for which problems we can get f of k times n. This is the area that is called fixed parameter algorithm, another very important area in algorithm design. And we are again mentioning for a general set of problems, we can obtain we mention how for a general set of problems we can get fixed parameter algorithms. Okay. Now, let's mention the simplifying graph decomposition theorem. So this is the paper that we had it with Eric Demain and Kenichi Kobayashi in 2005, Fikes 2005, and that's the result. It says that any H-minor free graph, by the way, what's the meaning of H-minor free graph? It means a graph that does not have H as a minor. Again, for example, you can say planar graph is a K33 minor free graph or K5 minor free graph. Here we say that as long as H is a fixed graph. Note that if H is not a fixed graph, then any graph is a minor free graph. But we'll say for any constant size H, the large class of graphs, which are H-minor free graphs. Again, this is a very large set of class of graphs. It's considered planar graph, bondage genus graphs, lots of other classes of graphs. So for these large classes of graphs, property, any H-free graph, can have their vertices or edges partitioned into k pieces. K is something, is an input. For any k, I can do this partition. So I can partition the edge set or the vertex set into k pieces, such that if you delete any of these sets in the partition, the other k minus 1, take the union of them, then we have a bonded Trivets graph. And this algorithm can be essentially done in polynomial time, so we can construct this way of essentially coloring or partitioning the vertices or edges into k sets in polynomial time. And for p-tests, the one that I will discuss later, you usually put k equal to 1 over epsilon. So if you want to get epsilon approximation, 1 plus epsilon approximation for a problem, then you will put k somehow proportional to 1 over epsilon. You will see some example later. Okay, so that's the meaning of, that's the first simplifying graph decomposition. Here, as you see, for example, we have deleted this one, then the rest have a bonded Trivets. Okay. Let's see an example. The graph coloring or chromatic number. Lots of you are familiar with this concept. So we know that the chromatic number, or essentially the minimum number of colors that you need to color the vertices of the graph such that for any edge the two endpoints have different color. It's actually a very hard problem. So you can prove that you cannot get anything better than n minus epsilon approximation unless some complexity assumption happens. What's the meaning of that? It means that essentially the best approximation, you cannot get anything non-trivial for this problem. If you want to solve it for general graph, you can simply give one color to each vertex, and that would be essentially the best type of approximation algorithm that you can get. You may get some greedy algorithm or something, but because of this result, provably on some graph they are as bad as this simple and naive algorithm that I have mentioned. So for general graphs, you cannot do anything. Now, I want to say I can give a two approximation algorithm for chromatic number in essentially, it is a out H-free graph. For now, just forget about out, it's just more general than H-free graph. For H-free graphs, using the decomposition that I have mentioned, let's see how. I want to get a two approximation algorithm for coloring on any H-free graph for a fixed edge. Okay, so let's use this algorithm that I have mentioned in the previous case. So let's just put k equal to 2. What's the meaning of that? It means that we can partition the vertex set into two sets such that each of them has a bonded Trivets. Okay, let's do that. So these are the two sets, and we will just delete any edges in between. We just consider the induced graph on each of these vertices. We have two vertices. Now, we have two graphs. What's good about it? The good thing about this algorithm or this approach is that now this graph is a bonded Trivets graph, if you remember. So I mentioned that if you remove any of them, it means that just you remain with the other graph, other vertex, then it has bonded Trivets. So what's good about bonded Trivets? The good thing about bonded Trivets is that it is algorithmically simple. It means that you can, because the graph has bonded Trivets, I mentioned that for trees you can find the best coloring, essentially two coloring. But for bonded Trivets graph, also you can find the best coloring in polynomial time. So what do? For each of this graph, we can find the optimum solution. Good. By the way, it is also important that we know that the optimum solution for each of them is less than the optimum solution for the whole graph, because this is just a subgraph of this graph. So, each of them is essentially a subgraph of this graph, and we can find the optimum solution for that, for each vertex set. Now let's find the optimum solution for these two graphs, both of them in polynomial time. And then how can we combine them? Just use different set of colors here and different set of colors here. Okay, how many colors do we use in total? I want to say that we are using at most 2 times the optimum of the whole graph. Why? Because we know that for this graph we are using at most optimum, for this graph we are using optimum, and then we are just putting together. And when you put them together, then the edges that you will put in between, because this set of colors and this set of colors are different, they don't cause any problem. So we have a valid coloring and at most 2 times optimum. And that was actually an interesting result that we obtained in 2 approximation for a chromatic number in this problem. And if you heard about Hajiaghayi's conjecture, Hajiaghayi's conjecture is a very important conjecture in graph theory. He said that any H-minor free graphs can be colored with size of H-1 colors. Here we are very far from proving this bound, even I don't know, H times some function of H is maybe not known. But here we said that, okay, not only maybe for this graph that you mentioned, you will say it can be colored with size of H, number of vertices of H-1. I indeed find 2 times the optimum solution for that, which might be much better than size of H-1. Note that he said that at most size of H-1 is needed, but it might be the case that you can get much lower number of colors needed to color this graph. Anyhow, so this is very important because of the Hajiaghayi's conjecture. We can get a 2 approximation algorithm for this, 2 times the optimum solution. Okay, another problem which is important, independent set. What is the independent set problem? In the independent set problem, you want to, you are given a graph, you want to find most number of vertices that there is no edge in between. For example, here you can see independence. So, using this theorem, I want to give you theorem that I mentioned. I want to say there is a p-task in H-minor free graphs using decompositions into 1/epsilon pieces. How? I will just consider the whole graph. For each I, so I will put epsilon k equal to 1/epsilon. So I will partition the graph into k, which is essentially 1/epsilon pieces, the vertex set again. Now, each time I will delete one vertex set and I will consider the k minus 1 other vertex set, and the union have bounded to it. So I will find independent set in the rest. So when you delete one part of one of these k sets, you know that the optimum solution in one of these sets, because there are k is equal to 1/epsilon, in one of these sets, select at most epsilon fraction of the opt. So you will just try all possibilities. You don't know in advance which part is that one. You just try all possibilities, and you know that in one of them, optimum selects at most epsilon fraction. But when we deleted this vertex set, then the rest has bounded trees. For bounded trees, we can solve independent set in polynomial time, finding the maximum independent set. So essentially, we are finding the optimum except maybe this epsilon opt. So we are using epsilon opt, and we get 1 plus epsilon approximation for this problem, which is a p-task. Okay. So lots of problems are closed under contraction but not deletion. Essentially, in minor, we say that two operations we consider it both deletion of an edge or contraction. But if we just want to strengthen our result, we only need to consider one of these operations. Deletion would be more like a subgraph, we don't consider it. So we only consider the contraction. What's the meaning of that? This is the more stronger result that we have for contraction decomposition. It says that any H-minor free graph can have their edges partitioned into K sets, such that if you contract any one piece, then the graph has bonded trees. Note that here for vertex set doesn't mean that much that you are contracting a vertex set, but for edge set it makes sense because you are just considering all edges which is in this particular set of the partition, and you contract it one by one, and at each operation if there is a multiple edge or self loop you just delete it. Okay, so this result, first, somehow the idea mentioned by Klein, not exactly this result, but then it has been generalized for bonded genus graph and H-minor free graphs and apex minor free graphs essentially, and this is the theorem that we have. Okay, so note that here we don't delete, for example, as you will see here in this example, we contract one part and the graph has bonded trees. So in some sense we are preserving the structure of the graph much more here essentially. So as a result here we have p-tested for several problems like traveling salesman problem that was a decade-old problem, or CH connected submultigraph, or we have fixed parameter algorithm for k-cut and bisection. I will mention some of the ideas here. So, fixed parameter algorithm via contraction decomposition. What is the k-cut problem? In the k-cut problem, you are given a graph, you want to delete, say the graph is connected, you want to delete the minimum number of edges such that the remaining graph has at least k connected compound. Okay, now I want to essentially obtain a fixed parameter algorithm for this graph on H-minor free graph. Note that we know that average degree of an H-minor free graph is at most square root of h times log of h. So some function of h essentially. It means that there is always one vertex of degree at most this. So we will just consider that vertex. We can just delete all edges of that vertex. Then we can find another vertex because the remaining graph is also H-minor free graph. So you will find that vertex and delete it, and so on and so forth. So you know that the optimum at most is this average degree times k. It's at most that one, because if you delete, you have at least this k vertices. Now, how can we find the optimum solution now using this essentially understanding? We are doing that theorem, the contraction decomposition, into C of h times k plus 1 layers. So the number of sets that we want to partition would be C of h times k plus 1. Now, we know that because this is at least 1 plus optimum, optimum at least in one of these sets does not select any edge. What's the meaning of that? It means that those edges, optimum does not delete it. It means that all of them can be contracted without any problem. So we can just again guess all possibilities and then find the optimum, find the minimum among them. But when you know that in one of these sets, the optimum does not select any edge, so you can contract it safely. But when you contract it, the graph has bonded trivets. Because the graph has bonded trivets, then you can solve the problem in polynomial time. So the running time of this algorithm would be 2 to the k times n, plus some n to the order 1. Essentially, as you will see, the running time is just 2 to the k times f of k times n to some constant which is independent of k. The fixed parameter algorithm. Just give you another example, fixed parameter algorithm for bisection. In this problem, what is a bisection? You want to divide the graph into two equal parts with minimum number of edge deletion. So you want to delete the, say the graph again is connected, you want to delete the minimum number of edges such that the graph, essentially, the remaining graph has the remaining graph has exactly two equal sides. And again, say the number of vertices of the graph is even. If it is odd, then you can be different by at most one. Okay, so for this one, again, this is again nice problem, which is closed under contraction. It is not closed under contraction or minor, but still we can use this algorithm. Why? Again, say consider the optimum solution for this problem. You can guess the optimum solution. So we want to say that whether there exists set of k edges such that you can remove them, and then the graph divides into two equal parts. K is the optimum solution. For any k, you just essentially using this partition into k plus 1. Now, sets. Now you know that again, optimum in one of these sets does not select any edge. When does not select any edge, it means that all of them will be connected. It means that you can contract it. Contraction essentially keeps connectivity. So we can contract them, then the graph has one derivatives, we can solve it optimally. So that's another example. That's for fixed parameter algorithms. Essentially, this is a theorem that we say that for any minimization problem, with the following properties, we can get approximation algorithms via contraction, decomposition. In particular, we can get p-tasses. So these are some properties that should be, the problem should be closed under contraction. It means that when you contract an edge, the solution size should not go up. It should be polynomial in graphs of bounded derivatives. It should have some spanner property. It means that if there is a graph G, you can construct another graph G prime such that the G prime somehow is a sketch of G. It's smaller than G, but somehow preserve the optimal solution there. So the weight of the G prime should be somehow proportional to the optimum of G prime. And at the same time, optimum of G prime and optimum of G should be very close to each other. This is called a spanner. In a sense, you can say this is a sketch of G. It's a smaller, essentially, graph that considers G and has properties of G. And finally, if you obtain, if you have an optimum solution in a graph G, that some of the edges, say a set S of edges has been contracted, now you should be able to get a solution to the whole graph by the cost of that optimum solution plus order of weight of the vertex set, the edge set of S. This is a general theorem. In particular, using this theorem, you can get application for TSP. For essentially, we can get a, this is just a special case of the previous theorem, we can get p-tasses for traveling salesman problem in weighted H-minor free graphs. And this is the result that we obtain it. And this is essentially the idea. The properties that I have mentioned, all of them are satisfied. The most non-trivial property is this one, that if you have a graph, the last one that I have mentioned. So if you have a solution of the graph, in a graph which is some of the edges are contracted, when you open it, somehow decontract this graph, then you should have a solution such that the size of this solution or the weight of this solution is the previous weight plus some constant times the edges that have been contracted. For example, here, the whole thing has been contracted into this one vertex. When you open it, you have a tour of the whole graph. Now you want to make a tour of this graph. So here you need to do some trick essentially. You need to essentially consider, you need to consider some Eulerian tour of this particular graph that has been contracted. And then twice of that. And maybe again you may want to add one more such that make the whole graph Eulerian, and then you can find the traveling salesman problem. Traveling salesman problem is essentially the problem that you want to start from one vertex, go through all vertices of the graph, and then come back to the same vertex. Note that here, one edge you may traverse it several times, and you want to minimize the length of this tour essentially. Essentially, that's the idea. The last one, as I mentioned, the contraction part somehow is the most non-trivial part, but that was a 10-year-old problem that we could solve it easily using this theorem, decomposition. So we have seen so far the applications of the minor decomposition. Then that was also applications of contraction decomposition. And essentially, for several other problems, so sometimes the contraction part can be tricky, but not that much tricky. The spanner part, the one that I have mentioned, you need to find somehow the sketch of the graph, a graph such that the size of that is only proportional to the optimum solution, and still the optimum solution here and the optimum solution in G are somehow very close to each other, 1 plus epsilon. That's the part which is a bit harder part. And for some problem we have constructed this one, but still several problems that we need to construct. Okay, so that's essentially I defined the minor decomposition, contraction decomposition. Let me just give you some ideas about the proof. I cannot go through the details because there are several lengthy papers, so I just want to give you some ideas. Okay, so the idea essentially is first we could prove this theorem for bonded genus graphs. And before that, we could essentially mention it for planar graph. For example, this is the theorem that we have it for bonded genus graph. So for bonded genus graph, the edges can be partitioned into k pieces, such that contracting one piece results in a bonded trivets. However, if you divide it into k pieces, then you delete one, the trivets would be this number, and it can be computed in this time. So this is an explicit construction. Okay, so let me give you some ideas about essentially how we can construct this one for planar graphs and bonded genus graphs and beyond. First, planar graphs, so that gives essentially the idea. For planar graphs, somehow these are some of the more details, but let me give you the idea essentially. So for planar graph, somehow the most representable graph of planar graphs is a grid, n by n grid. So this is essentially, we have n rows and n columns. And there is a vertex in the intersection of each of these rows and columns, n by n. That's somehow the base representative of planar graphs. Now consider this graph, n by n grid. So if you want to construct essentially this kind of the minor decomposition, what do you do? So you consider so how can we get essentially this k vertex set? So essentially you will start from the top, and for every, so consider you want to say construct k sets. Now, for every I mod k, you will just remove the edges on row I mod k. So if you have, this is the first one, this is the second one, you are deleting one row here, and one row here. So for each I, essentially, you are removing this edge set. And that's the way, essentially, that gives you that's the way that you can get this theorem. I mean, you can say it in another way. For a general planar graph, you can consider one vertex, any arbitrary vertex, and then from this vertex, you are doing a BFS, best first search of the whole graph. Then, to obtain essentially the vertices that are going to class I, you only need to essentially consider all vertices whose distance from this root is I mod k. If you want to construct k essentially sets, again, all vertices similarly, you can say for edges also, all edges which are essentially attached to these vertices of I mod k. So for those guys, those are the vertices that go to set I. And for each I, you are doing that and you are creating these cases. So that's essentially the idea. So that's essentially the idea for graph mining. Now for contraction, you need to do more complicated things. You need to consider this grid that I have mentioned. You need to consider the dual of this grid. And for the dual of this grid, you need to, again, the dual of a grid would be a grid. And the dual for each face, you are putting one vertex, and then two vertices in this new graph will be connected if they share one edge. But essentially, a dual of a grid would be another grid. Now, and you know that the deletion on the dual is corresponding to contraction in the primal, and vice versa. So that's the whole idea. Instead of essentially you are deleting the edges in the primal, first you are creating the dual of this graph, then you are deleting the edges in the dual. But if you delete edges in the dual, they are corresponding to contraction in the primal. So essentially you get this result for planar graph via this approach. This is essentially the main observation that Phil Klein made it, but not with this definition of contraction. He called it compression. Anyhow, that's the idea for planar graph. Now for bonded genus graphs, the issue that you will see here, you have essentially when you have genus greater than 1, then you might have essentially some handles. And now, so the graph is not just planar, but it's some handle. You need to cut this handle. You need to do a little bit topology here, essentially, or graph topology, such that you will cut these handles. And essentially, when you cut any handle, you may increase the tree width. So the tree width will not be as good as planar graphs. That somehow would be some function of g. If you remember here, I mentioned that the tree width would be not just k, would be g. So essentially, you need to cut handles. And how many handles do we have? Essentially, g handles. And each time that you are cutting a handle, essentially, you are increasing the tree width by this one. But essentially, the same algorithm that I have mentioned also works for planar, for bonded genus graph. Again, for bonded genus graph, you can do this one. If you want to get for deletion, you just consider one vertex. You are doing some DFS essentially, some BFS from this vertex, and all vertices of mod I distance from this vertex, mod k. So that would be I mod k. Those are the vertices that go to set I of the partition. The partition has I sets. That's essentially the idea for bonded genus graph. So I just make it formal here. So let's go for the, okay. However, for H-free graphs, actually the theorem would be much more complicated. Why? Because of this theorem of essentially, this is graph minor 16. So 16 paper in this series. They essentially, Robertson and Seymour proved that any H-free graph essentially is somehow a tree of almost embeddable graphs. Almost embeddable graphs somehow are bonded genus graphs, but a bit more complicated. For example, this is an almost embeddable graph. You have a bonded genus graph. You have a set of constant number of parts, which is called vortices. They have bonded path widths. Bonded path width is somehow a special case of tree widths. So these are non-planar, but a bonded number of them. And the path widths or tree widths of them is bonded. And you have a bonded number of apices. These are the vertices that are outside of this surface, and they can connect to anywhere. But again, their number is bonded. So the graph is a tree structure of these graphs. And what's the meaning of exactly tree structure? How to combine them? In a sense, you will decompose these graphs via this operation which is called essentially click sum. The click sum of a graph G and G1 and G2 essentially is a graph that, so you consider a click here, both of them should have a click, and then when you put them together, then you can delete some edges. That graph G is called G1 plus G2, the click sum of this. Essentially, Robertson's theorem says that any graph, any H minor free graph G for a fixed edge is a click sum of almost embeddable graphs. So a set of click sums of almost embeddable graphs. As I mentioned, almost embeddable graphs are bonded genus graphs. So the way that I have mentioned, you can construct essentially the partition there for bonded genus graph. However, we have a problem when we have a click sum, and that's essentially the hardest part to prove this, especially in contraction theorem for H minor free graphs. For minor version, minor decomposition, that is not that hard. Why? Because when you delete an edge, then you can delete these edges in any of this graph also, and you are allowed to do deletion in minors. However, in contraction, you are not allowed to do deletion. And that's the problem essentially that we have it. So essentially, when you delete some edge, then this will be destroyed. You cannot contract this edge anymore. If you put it in one of these, so you may have it, essentially we try to construct inductively for G1 and G2. Here, for example, in G1 and G2, you may give some, I don't know, layer or some color I to this edge and to this edge. And that so far is good, but means that it should be contracted, this guy. But when you do this operation, this edge will be deleted. So you cannot contract it anymore. And the contraction is very important. So that's essentially the part that makes the, essentially the proof much harder. And you need to somehow create or recreate these edges. So here, for example, if you have a click sum, now you need to use more structure. You can say that this click sum essentially happens mainly with the click of size 3 on the surface. So it's not that bad, but still you need to create these 3 edges. So the issue is that these edges will be deleted. You need to find some path here such that somehow A to B and B to C and A to C, such that you can contract this path to create these edges. Okay, so that's the idea, but it's not so easy. The proof is quite complicated essentially here. So here, what do we do essentially? We are finding 2 paths from A to B, and then 1 path from C to essentially this AB path. So 2 paths from A to B, 1 and 2. And then from C, we have 1 pass here. Now, if you see, then you can contract everything. You can contract everything to make essentially this click. But then you need to make sure that you can actually create these passes. And that's the part that essentially makes the proofs much more complicated. So you need to do essentially some complicated stuff. And this is the theorem that essentially we are using. So this path that I have mentioned from A to B, essentially there are 2 shortest paths. And we need this theorem that we are proving that the 3 bits of radius are neighborhood of order 1 shortest path is order f of r. So if you consider r shortest path and then consider r neighborhood means all vertices at distance r, then this is the theorem that we prove. It is non-trivial, the proof essentially, that the 3 bits would be f of r. So, and essentially, and the shortest path is very important. If it is not the shortest path, for example, consider this path has 3 bits essentially 1. But if you consider the 2 neighbors of that, that would be ordered. Anyhow, that's the idea essentially, and this is the idea of the proof. I don't want to go through the details of this, but before that I want to say essentially 2 main open problems. So we have mentioned this theorem for H minor free graphs. The whole idea is that can we generalize this for more essentially general graphs. So we could prove, for example, for odd minor free graph, which is a generalization of H minor free graphs, and for the case of k equal to 2. So we can, for odd minor free graph, we can partition the vertex set or A set into 2 sets, such that each of them, if you delete each of them, the graph has bounded derivatives. Again, not for any k, for just 2 and odd minor free graphs, the generalization of H minor free graphs. Can we get it more general? So we could prove it for H minor free graph, but that might be true essentially for much more general class of graph. And then all these applications that I have mentioned, you can get it essentially for those problems. Finally, this thing that I have mentioned, this framework for spanner construction. So here the main challenge is essentially using the simplifying decomposition, is to construct the spanner. As I mentioned, in the decontraction part, you might be able to solve it somehow, but for the spanner part is quite non-trivial. We had a few papers essentially just for creating the spanners for different problems, and still this is a very nice area to work more and get a general theorem. These are essentially the main problems that I wanted to mention, and essentially thanks everyone again for attending this talk, and I hope that you enjoyed it.